So hi everyone. Yeah, we have Maan Hani, who's from University of Victoria. He works. He's a graduate student, and he works with Sarah Ellinson, and he works on simulations. And today he'll tell us about galaxy mergers molding the circumgalactic medium.
Thank you. Thank you for hosting me here today, and it's my pleasure to be here to share some of my research with you. I'm hoping this will be a more casual, informal kind of style seminar. So if you feel free to disrupt any moment and stop me and make me explain things or challenge some of the ideas that I'll be pitching. After all, I'm a theorist, so it's all right to do so. It is kind of interesting because I work with an observer, so a lot of the work you'll see today is from simulations. However, it's motivated or it's done in an observer-friendly way. So you may think it's weird that we're doing things a certain way, but hopefully I'll motivate it and I'll motivate why we're doing the work we're doing. Before I even start, I have to thank a bunch of people without whom this work would not even be possible. Martin Spar, Paul Torrey, Mark Vogelsberger, and Volker Springel. They have been great support and they've given me tremendous help. So thanks to all of them. So as the title says, I'm going to hopefully tell you today how galaxy mergers mold the circumgalactic medium. But just before we start, a bit of a roadmap of what we're going to be doing today. First, I'm going to start with the current status of the circumgalactic medium, what we know about it so far, how we think of it, and what we understand of its properties. After that, I will briefly touch on some of the main results of what galaxy mergers are known to do and induce in galaxies and how they affect the evolution or the life of a galaxy. After that, I will motivate what we're working on, which is the connection between galaxy mergers and the circumgalactic medium in the context of two main points. First, the content, metal content of the circumgalactic medium, as well as ionization, which is usually observable, and then in the context as well as how merger-driven outflows change the properties that I already mentioned. Finally, I'll conclude with some remark and tell you a bit about our future plans, which I would love to discuss with you after, if you're interested. So for starters, the way we think of the circumgalactic medium is effectively depicted in this great image from Jess Work's talk recently. And the galaxy is in the center, and what's happening is this mess around it is what we think of as the CGM. It's really the righteous gate of passage for any gas that wants to accrete its way onto the galaxy, form stars, or just settle into molecular clouds. Also, it is the liaison between the galaxy and the intergalactic medium where this pristine primordial gas hangs out. So if gas wants to be ejected from the galaxy by some mechanism, needs to go through the circumgalactic medium and interact with the gas that's already there. Moreover, some of the gas that gets shooted out through outflows, fountains, whatever you want to call them, will mix in the circumgalactic medium and maybe have enough time to cool and settle back down onto the galaxy if it's not ejected with high enough velocities to escape the CGM. So that's just the cartoonish picture of what we think of the circumgalactic medium. And recently, how people have been studying is the CGM is very different from the past. In the past, people looked at quasars in the background. They saw some absorption, and then they started to look at neighboring galaxies to associate the absorption with the host. More recently, in the last 5, 6, 7 years, things have changed, and that's all thanks to HST and the cosmic origin spectrograph on HST. So the game has changed in the way that we started selecting galaxy-quasar pairs and studying the absorption associated by that galaxy's given redshift in the quasar spectrum. And the question we're asking now is a bit different. We're asking, what does the CGM of different galaxies that have some galactic properties in common change? And there has been a plethora of COS spin-offs that have surveys that have made a huge difference in our understanding. So far, we know the circumgalactic medium to be a clumpy medium, where they have some, I call it warm here, but you can call it cold if you want, depend kind of what astrophysicist you are. So 10 to the 4, 5-ish gas, that's relatively clumpy, and then that's embedded in a hot diffuse medium around it. We know that from various observations. We also know that there's a significant amount of gas in the circumgalactic medium. So just work in 2014 and most recently Prochaska et al. In 2017 have integrated the amount of gas in L-star-like galaxies out to 150-ish kiloparsecs. And they found that the CGM, which is anything, if you want, above 50 kpc or 60 or 70, you can pick the inner edge you want, has a significant amount of gas in the galaxy, and it contributes quite a bit to that reservoir that we have. Moreover, Molly Peoples, I don't have the reference here, unfortunately, but Molly Peoples has broken down the gas in the galaxy into its different components. So you can see that some gas resides in the disk, but a significant portion of the gas related to its cool, hot, and warm, hot CGM contains quite a bit of the gas. A significant fraction of the gas, in other words, hangs out in the CGM. And that gives us a bit more of a push to actually care about that reservoir that's surrounding all of these galaxies we know about. More recently, Prochaska showed that there's enough metals in CGM to care. So they have selected, CosHalos has selected 32 systems, which are all L-starish, and they have compared the metallicity of the CGM with the metallicity of distribution of just L-star galaxies in their disks. And what you can see that the green, which is your CGM, does not have any low metallicity tail. In other words, you are not observing this low metallicity tail, and that could be maybe that you're biased. However, you are observing a high metallicity end, and there's about 25% of your sample that has supersolar metallicities, which is quite interesting if you're trying to account for the metals in the universe and look at the metal budget of galaxies. Molly Peoples went and added all the metals you see in galaxies, and she showed that about 80% of those metals actually are not in the galaxy, they're in the CGM, they're just sitting there. She was able to account for a bunch of them. However, there's still a tiny fraction that's missing. Maybe not so tiny, but there's a fraction that's still missing. But there's enough metals in the CGM to motivate studying it if you care about the history of the galaxy or the future of a galaxy, in other words. And then some studies have shown early evidence of enrichment. Theorists have shown it many times, but I'm trying to stick with observations for the motivation for now. And we can see that in Prochaska's recent paper in 2017, there is this kind of decreasing trend of metallicity with hydrogen column density. And what that has been referred to is that you have early evidence of enrichment in the galaxies where this low column density hydrogen has been more enriched than this high column density hydrogen that you observe at these larger distances in the CGM. Now, everything I've talked about is about the CGM, but there really is a relationship between the CGM and the actual galaxy. And the COS gas survey led by Borthacker et al. In 2011 showed that the CGM H1 content, just H1, actually correlates with the H1 content of the disk of a galaxy. So they selected galaxies where they've had gas results for them, and they looked at their CGM using COS, and they compared the two results, and they showed that there is a positive correlation between your H1 content in the CGM and what the actual galactic disk looks like. So far, we've learned a lot about the CGM. However, it has all been from the point of view of isolated galaxies. All these studies I've showed, or I mentioned, and I didn't mention a lot, they've all selected galaxies based on some kind of isolated criteria. So not many people have looked about what galaxy pairs look like or what galaxy mergers do the CGM. And one thing that we know for sure is that mergers are a great way to evolve a galaxy. You can change the morphology of the galaxy significantly. You can grow the stellar mass of a galaxy, grow its gas reservoir, or deplete its gas reservoir through single merger. Studies have shown that if you merge two galaxies, you have some kind of gas redistribution that shows usually as a metallicity dilution in the center of the galaxy. It's been shown in theory. It's also been shown in observations. So Allison et al. In 2013 selected galaxy pairs, kinematic galaxy pairs from SDSS, and they showed that if you plotted the metallicity in the central fiber from SDSS versus your pair projected separation on the sky, the closer the pairs are, the lower the metallicity is in these galaxies if you compare them to a control sample that's mainly isolated. So that's telling you that the merger, or the interaction between the two galaxies in this case, is affecting your metallicity profile in the central disk of the galaxy. Also, similar studies by Dave Patton in 2013 showed that there is an increase in the star formation rate in the central regions of the galaxies that are in pairs as a function of pair separation. So same idea, pair separation to the right, and SFR enhancements relative to a control sample. So 1 means no enhancement, and the galaxies look exactly like the control sample statistically. And you can see that both in simulations in the red and in the SDSS fiber in the blue, there is an enhancement towards pairs with lower separation. In fact, there is an enhancement out to around 150 kbc or so that is observed in galaxy pairs in star formation. You can do the same thing for AGN. You can go select SDSS galaxies that are isolated. You can select SDSS galaxies that are in pairs and look at the AGN fraction. And what you can see is that there is an enhancement in the AGN activity as a function of pair separation, also extending to many tens of kiloparsecs in pair separation. So what that is really telling us is that galaxy mergers affect the galaxy. They affect some physical processes that we all know and love, and we all know they affect the galaxy in some ways, in enrichment or outflows, or other ways, like star formation and AGN activity. They affect what the galaxy looks like morphologically. So we've seen tails that extend to many tens of kiloparsecs in hydrogen, in H1 gas, and in stars in galaxies that have merged. We've seen train wrecks just by pretty images we use for outreach. And we know that the shape of the galaxy is affected. In fact, tidal tails extend well beyond the galaxy merger time. And some theoretical studies showed that outflows from the actual central galaxy can survive for many, many gigayears, depending if you choose your parameters right. But they can survive for a long time after the merger or after the outflow has been launched into the CGM. So in other words, I'm trying to make this nice picture for us all here. I'm trying to say that galaxy mergers affect your galaxy. The CGM is this unknown region around the galaxy that we're starting to learn about recently, thanks to the COST surveys. So how do the mergers affect the CGM? If mergers are good at launching gas, if mergers are good at messing out the morphology of the galaxy, in fact, changing a spiral to something that doesn't look so spirally anymore, and if mergers are good at inducing star formation and AGN activity, which we all know are really good mechanisms for depleting the gas, launching the gas out of the galaxy, and sometimes into the intergalactic medium. So how do these mergers affect this medium that's in the middle between the intergalactic medium and the galaxy, or just surrounding the galaxy? So effectively, this is the questions we're trying to answer, is if we have a CGM, what does the merger do to it? And we think this is a key piece of a puzzle if we're trying to understand galaxy evolution in general. So technically, this should be simple. You should be able to take a galaxy merger, trace the properties of the CGM during the merger, and we understand the interplay between the galaxy and the merger. Now, unfortunately, that's not so simple in observations, just because you are at the mercy of Mother Nature. So you need mergers and quasars to overlap effectively. And the problem is that mergers in our z = 0 redshift 0 universe are very rare, let alone mergers in front of quasars. So that poses a very big problem for observations. Nonetheless, some galaxies can be found, or some kinematic pairs can be found in front of galaxies. So why not do it in simulations? And that's our approach that we've taken. So what we've decided to do is use cosmological simulations for a bunch of reasons. First, we're not at the mercy of any quasar pairs. We can place our quasar wherever we want it. Second, we don't care about the sample size because we can create as big a sample we want. And third, most important, is that you can trace the CGM wherever you want. At any point in time, you can slice your universe and look at the CGMs of galaxies. Moreover, you can trace the CGM prior to the merger, post-merger, slightly post-merger, 10 gigayears post-merger if you feel like it, and run into the future. You can do all that, and you don't have to make any assumptions about the structure of the merger, the CGM, because, well, we're using cosmological simulations, so hopefully the accretion history of the galaxy has taken care of that. Now, of course, the downside of all this, you're not dealing with the real universe. So you have some assumptions about the physics model you're using. And we all know the diversity in the physics models out there. There are some assumptions about the feedback that you use, some assumptions about how you deal numerically with your gas. So if you have a different kind of code versus like an SPH code versus a grid code and so on. So we have all these problems, and we have a resolution issue that we also have to deal with. However, we still have an upper hand on observations in all the other motivations that I mentioned. So we're going to go through and use cosmological simulations. Our weapon of choice in this case is the illustrious box. So we took the illustrious 1 box, and we've selected galaxies from it. Well, I haven't selected them. So Martin Spar has done so in his 2016 paper with Volker Springel. And they've selected galaxies from the illustrious box, and they reran them at 3 resolutions, the highest of which being 40 times illustrious in mass. And the way they selected the galaxies is such that your redshift 0 descendant of these galaxies, these mergers, is a Milky Way-like galaxy that's relatively isolated. And the merger has to occur between redshift 0.5 and 1. Of course, there are some mass cuts on when we say Milky Way, so dark matter or M200 and stellar mass and so on. And if you care more about the details of the sample, I'll be happy to discuss it later. So Martin had 4 simulations after he did all these selections. For us, we will use only 1. Because the choice of merger does not really matter after all. We've checked all 4. They all give qualitatively the same results. So we'll use 1 just to highlight the effect of the merger. And then once I get to the future work that we're planning, hopefully that will make more sense as why we're only picking 1. And if you're interested about what physics models we have, so we basically have the illustrious model plus some extra physics, which is more recently the Auriga model that came out in Grant 2016. It's quite similar or comparable to the new illustrious model, the 2nd generation illustrious model. So briefly, we have some metal enrichment that comes from supernovae, AGB stars, and supernovae type 2. We have supernova feedback in the form of winds that are being launched from the star-forming gas. We have AGN feedback that we break into quasar and radio mode. And we have, of course, radiative heating and cooling. The cooling is both primordial and metal line cooling. And our heating is from a UV background that's redshift dependent, but isotropic other ways. And we have an AGN component to our heating, which will come in handy later on as I describe the ionization of the gas. Okay. So once we have the simulation, what we can do after that is do whatever measurements an observer can do on a galaxy. So what an observer does is they pick a galaxy, they have a quasar somewhere around it, and they measure some absorption. And then they pick another galaxy and do the same thing, and another galaxy and do the same thing. And then they collect a sample. Now, one assumption that observers make all the time is that the CGM of all these galaxies that have been selected on a mass criterion or something or luminosity criterion is the same. That's how we can calculate covering fractions for gas and so on. So instead of picking 30 galaxies, you can pick 1 galaxy and put 30 sightlines in it at different impact parameters or distance from the central galaxy. These 2 operations should be the same if our assumption is true, and we have good reasons to assume that the CGM is relatively similar between similar galaxies, which may not be really true, but we have good reasons to assume it. So we've picked 1 galaxy, and we poke random sightlines through the CGM around it. And then we can count how many of these sightlines pass through absorbers of a given column density. And if we know that, we can then learn something about what our covering fraction is, or we can learn about the density structure of the CGM. So for starters, I'm going to start doing that. So I'm going to look at the covering fraction evolution throughout the merger. So we're going to start with a pre-merger galaxy and look what happens at to its CGM as we go in covering fraction. Okay. So on the left, there's oxygen. On the right, there's hydrogen. I'm going to spend some time explaining the oxygen plot, and the same applies to hydrogen. So the different colors are different cuts in your column density. So if you're an observer, these will be different cuts in your line width or equivalent width of a line. For us, it's just a column density cut because we can do that. And everything is normalized to a pre-merger time. So we've taken some number of mega-years pre-merger that the CGM looked very stable, and we've averaged the properties of the covering fractions of these different absorbers in the CGM. And then after that, we started to look at this new covering fraction relative to the pre-merger covering fraction for different absorbers. So 10 to the 17 per centimeter squared would be your highest column density for oxygen, and then for us 10 to the 15 is the lowest we're tracing. But keep in mind, these are total gas column densities. These are not any ionization species in particular. So if you're used to looking at H1, for example, or O6, or some specific ionization, these do not hold because you won't see these high column densities anyway. All right, so we have a characteristic shape for all these curves. So the dashed vertical line is our merger time based on what the black holes are doing in the central of these galaxies. So we have an increase in the covering fraction here, which we understand quite well. Effectively, you have a given size for a projection box, which is your field of view, which for us is 300 kpc by 300 kpc, which is equivalent to the typical impact parameters that are used in absorption line surveys. And then as the second galaxy enters your field of view, what you're doing is you're increasing the area that is being covered by gas. And this increase in the area corresponds to an increase in the covering fraction because you're increasing the number of sight lines that get intersecting gas of a given column density. So we have this increase, and as the galaxies start to overlap, you start to see a dip because you decrease the area after all, and then the merger happens. Okay, so this hump in the beginning is well understood. Over here as well, you see the same hump in hydrogen. However, what we're interested in is what happens after the merger. Now, post-merger is when you have this significant increase in the covering fraction of your highest column density gas and intermediate column density gas. And what's really happening is that as the galaxies merge, I'm going to use a very colloquial term here, you fluff up your galaxy. That's really what you're doing, is you have some tidal effects, you may be inducing star formation and so on, that will just push out the gas a bit. And as you do that, you see an increase in your covering fractions because you made your galaxy look bigger. Now, of course, if you were to keep going up in column densities and pick some absurdly high column density gas, you will not see that increase simply because you need your gas to be dense enough along the line of sight to see that increase. Okay? But that holds for most reasonable column densities. So you see that increase in covering fraction, and then that increase carries, well, it dips a bit after the merger, but it carries for a good time after the merger, for about 6 giga-years comfortably. After the merger, you can say that I have an increase in my covering fraction for my metals, and I can see that. There is a sharp dip over here, which I will talk about later on when I come to the ionization. However, for now, just let's assume this doesn't exist for the purpose of just right now. So you see this increase that hovers around factor of 3 or a bit more for your highest column density gas. But even if you go to the more diffuse but still dense enough oxygen, you do see an increase about factor of 2 that carries on for many giga-years post your merger. Now, if I was to move to hydrogen, unfortunately, you see that increase, but not as pronounced. So keep in mind, your CGM gas already has a lot of hydrogen to start with. So for you to see an increase in covering fractions, you need to pick the right covering fraction, the right column densities, but also you need to look at an area that wasn't covered by a lot of hydrogen to start with. So the lowest hydrogen column densities, keep in mind these are total hydrogen, see nothing, no change whatsoever. And that's telling you that every sight line you've passed in through the box has passed through these column densities anyway. So imagine just you have a diffuse gas that's covering your whole field of view, and it's just there. Okay. So anything that's changing is these higher column densities. So we expect the highest column density hydrogen to change, which is, whoops. We expect this to change simply because that is the gas that's in your disk. So the highest column density gas sits in your disk, at least in our simulations. And then for you to change it, you need to launch high column density particles, or cells in our case, outwards. And that's not easy to do. If you launch a high column density or high density gas cell into a low diffuse medium, you're going to diffuse that cell relatively quickly, and it's not going to hold. So you need to launch a bigger clump, which you do see. You are launching bigger clumps. So after a merger, you still see an increase in your highest column density gas, but not as much as pronounced as the oxygen, simply because you need a very high density clump to travel into the CGM. Also, these clumps won't survive as long when you launch them. Okay? So the size of the clump tells you how long it's going to survive in a given temperature or density CGM. And that is not a new story. It's been shown in simulations of single gas clumps traveling into the CGM. So effectively here, we're almost looking at low number statistics. So you can kind of ignore the red line. The green line, on the other hand, is where the interesting stuff happens. So after the merger, you see an increase in your green line, which is an increase in your hydrogen covering fraction. And then after that, you start to see that decrease. Okay? So what that's saying is that your galaxy fluffed up, became bigger. And then after that, this gas either diffused or came back into the center. And you don't see that increase in the global hydrogen covering fractions anymore. But that's total hydrogen. So that does not represent what's happening in the real universe, because we don't look at total hydrogen in the real universe. We look at just neutral hydrogen. Okay? So the hydrogen gas still increases, just not as much. And it increases for almost as long. So if you remember, this sharp dip here corresponds to this sharp dip there. And they're about like slightly delayed. But once we talk about why they're there, they'll make a bit more sense. Okay? So another way to represent this that's more reasonable, I guess, if you're looking at a galaxy profile, is to look at the column density profile or density profile of a galaxy. So on the left, I show the oxygen density profiles. On the right, I show the hydrogen again. The different lines are the different times of the merger. So pre-merger is 1 gigayear pre-merger. Post-merger is 1 gigayear post-merger. And the merger is this dashed line right here. And you can see that pre-merger, you have a very you have a normal metallicity profile inside the galaxy, and then the density in the CGM drops sharply because your gas in the CGM is not as metal rich. And after the merger, you see an enhancement in the central metallicity, which is normal. You are actually enhancing the metallicity of the gas because you're making a lot of stars. That's quite normal. So you see that. However, in the external part of the CGM, which we care about, so this is 10 kpc here, so you can look at 30 or 40 kpc outwards to 100 plus kpc. You see an increase in the metallicity of the CGM, or the metal content over here of the CGM. And if you just trust this section right here, which is not so large on a log-log plot, you can see that there is a propagation of that enhancement outwards. And I will show a plot later that will show that there is truly a propagation of the enhancement outwards in the CGM. So basically, you dumped your metals out in the CGM, and then as time went by, this metal had propagated outwards, which is a signature of outflows. And this is not a new story. Mergers produce outflows, so it's all right. However, we do see that here, which is good. So we can kind of understand why these metals are making their way outwards. In hydrogen, you still see the same effect relatively. You see an enhancement, post-merger, you see an enhancement in the hydrogen content in the center, which is normal. You're putting more gas into the central part of the galaxy, funneling gas if you want, but these are large scales. You're putting two galaxies together. After the merger, on the other hand, you still see that increase in the external amount of hydrogen, which is also typical of throwing an outflow outwards. You have metals, but also you're going to have hydrogen. It's the dominant gas, after all. Now, unfortunately, I'm not showing it here, but if you trust me, if you were to take the ratio of these two plots, you will get what is a metallicity profile of the galaxy. And you see an enhanced metallicity profile, a significantly enhanced metallicity profile in the outskirts or in the CGM in our case. And that metallicity profile propagates outwards. So I'm just gonna kind of summarize what we saw here. So we saw an enhancement in the covering fractions that lasts for many gigayears post-merger, which should be technically observable if we were to target galaxies asking what does the merger do. We do see an enhancement in the hydrogen profile launching to many gigayears, however, not as pronounced as the metallicity profile. Keep in mind these are relative to pre-merger, so that could be why. And if you were to create a metric, which we have, that measures the size of the CGM, so you can ask yourself, where in the CGM does my covering fraction of a given column density drop below some threshold, and create that metric and measure what that size is, you can see an enhancement in the size of the CGM. So the size of the CGM enhances by a factor of 1.5 to 2, depending which metal you're looking at, or hydrogen. So effectively, you're making your CGM larger. Okay, I'm going to skip over that metric because in the interest of time, and I'm going to show you the metallicity. So this is the metallicity plot I was talking about. Pre-merger, you have some metallicity profile, and it drops sharply in the outskirts of the galaxy. So this is really your CGM here. And after the merger, or a good time after the merger, you start to see this enhancement over here. So between 10 and 100 kpc, you see this dashed line is immediately after the merger. Okay, and really, this is merger and post-merger. And this dotted line over here is 1 gigayear post-merger, which is our post-merger time. And you can see that this metallicity enhancement propagates outwards to 150. And if you were to be bold and go even further, go to like 300 kpc, you see that enhancement propagating outwards, actually. And if you were to draw slices in your CGM, which we've done over on the right side, and trace the metallicity propagation outwards, you see that that propagation is delayed as it propagates outwards. So on the right, what we've done is we've taken slices inside our CGM. So the inner slice is this cyan line is your inner 10 kiloparsecs. And then this dashed line in the red shows the 75 to 100 kpc. So this is the outer edge of the bin. So 75 would be somewhere in here. And then your green line shows the 100 to 150, which is really your outermost CGM in our case. And you can see that after the merger, so the merger is the gray line again, you see an enhancement in the CGM, in the CGM metallicity, which keeps going and going and going. Although the amount of gas earlier dropped significantly after 12 gigayears, you don't see the drop in the metallicity, which is assuring kind of thing. It's not you're removing metals preferentially, you're just removing gas overall, which is kind of okay. We kind of have a reason for it right now, which may not be realistic, but we have a reason. So you do have an enhancement in the CGM metallicity. And if you just trust me, I have made the plot. I'm not showing it here. If you just trust me, there is a delay between the red and the green curve. So the red peaks before the green. And then if you follow what the red does, you see that the green curve does it slightly later, about couple of hundred mega years later, or a couple of tens of mega years maybe later. And what's happening here is that your gas is getting to your inner bin, enhancing your metallicity, and then diffusing and traveling outwards and enhancing the metallicity in the outer bins after all. So you see that propagation outwards. I would like to point out just this dilution in the central region of the galaxy, which has been observed. I mentioned it earlier, so Ellison et al. In 2013 has shown that there is a dilution in the central region of the galaxy, which is also reassuring. So we do see a 0.2 to 0.3 or 4 dex enhancement in the metallicity, or in O to H, for many gigayears post-merger, and that enhancement should hold. So other simulations have shown that outflows actually do enhance the metallicity in the CGM, and I will mention them later when I'm talking about.
What is the main driver of these outflows in the simulations?
So really good question. In our case, it's really hard to disentangle what's pushing the gas out because we can't really, it's not a trace. You don't have a particle to trace to see if it's launched from a star-forming region or, yeah.
On and off.
Correct. So you can turn on and off. I have not reran the simulations like with no AGN feedback to look what happened and so on. And the idea was to do this in the future to look at the details of what physics is driving what. However, you can see, depending how far the outflow goes, you can see what the driver is. And a lot of, I'd say the inner CGM is affected by our star formation, but really the outer CGM is mainly our AGN driving the gas outwards. However, the right way to answer this question would be to rerun by running multiple simulations, or rerun with some kind of tracer particles, which we are planning to do in the future to trace where the gas is coming from.
So these are not SPH simulations?
No, these are Arepo simulations. Yeah.
And just have a question. So what kind of supernova feedback is this? Is this energy injection or a momentum injection in the ISM after you?
After you launch your wind particle, you decouple it, right, from your hydro, and then you recouple it with dumping all your momentum.
Right.
Yeah.
So it's momentum feedback.
Yeah. So there is an energy feedback associated also with the other kinds of feedback, but the supernova type 2 is a momentum push. All right.
The deficit in metallicity in the center, is that just a mixing effect where you're pulling in the less enriched gas from the initial outer region of the galaxy?
Correct. That's exactly it.
That must be purely kinematical, I guess, right? You can't have feedback or AGN pushing that gas into the...
No. This is absolutely kinematical. It's been shown in observations as well. Is once you have a merger, you have tidal torque that's just remove your gas or funnel your gas inwards.
So getting back to Christopher's question, does this give you any indication how much kinematical effects are important for the driving of the gas around, as opposed to just the feedback?
So this, you can out in the CGM, you can see the difference between kinematics and feedback outflows simply by looking what happens to the stars, right? Because kinematics affect the stars too. And you really don't see any effect out. Like you don't see giant star streams flying to 100 kpc or any of that. It's just that the gas is being pushed, and if you, yes, so I'm going to just spoil it. If you were to look at the velocity profile of the gas, I don't know if the arrows are visible out there, but you can see that, so post-merger is right here, which is about 1 gig a year when you can start to observe these. You can see that your velocity profile is purely poking outwards. Even if I do a projection along, like pick your favorite axis, do your projection along it, you can see that your velocity profile is mostly pushing outwards in these directions. Before the merger, you can see kind of a overall pretty kind of gas profile. There is some outward directions, there's some inward directions, and so on. But if you look at the divergence effectively of your velocity profile, it's all positive, or it's mostly positive after the merger. Yeah. So that spoils this part. But these are the outflows I wanted to talk about. It's hard for us to say for sure if where the gas is coming from, simply because you have to rerun the simulation, either trace the gas by like Monte Carlo tracers, or really shut off some kinds of feedback and test what the actual feedback is doing. However, we know that outflows are responsible for some enrichment in the CGM. So Muratov in 2016 used fire. And they showed that early on, at slightly higher redshifts, you do have an enhancement in your CGM metallicity, which is purely being outflows driving your gas outwards, which is normal. We kind of, like in the back of your head, you'd say, okay, this is not surprising that the gas is poking your metals outwards, and you're supposed to see a metal-rich gas going outwards, not just primordial gas, just because you're launching it from metal-rich areas in the galaxy. So what we're blaming this outflow on is, so we're blaming this enrichment on is the outflows. However, to say definitively where the outflow is coming from, you would have to really rerun the simulation again. Okay. I have a tiny bit of time left, and I would like to talk about something more observable, just because my supervisor would be upset otherwise. So I need to talk about the ionization. So when observers go out and observe things, they actually observe certain ionization species. So you see some line that's due to some ionization species doing some kind of absorption, and that's how you see the lines. So for us, everything we've shown so far is from the point of view of total metals or total gas, and it's not really the most realistic way to go, because for observers to go from ionization or equivalent widths to column densities, it's not usually a simple transformation. So to create the ionization or to calculate the ionization, unfortunately we do not calculate the ionization on the fly. So there are some groups that do. So Ben Oppenheimer has done it many times. He has like an on-the-fly calculation of the ionization, and he does non-ionization equilibrium and so on. In our case, we assume equilibrium, which is probably a bad assumption, especially like maybe a few months ago, there was a paper showing that that's a bad assumption if you have an AGN. And we do some cloudy modeling, like the typical thing to do in the field. We include an AGN simply because it's included in the physics model, so you're affecting your radiation, your cooling timescales because of the AGN, so we include it. And we include UV background because, well, it does affect your ionization as well. We have some assumptions that are not the craziest. We have single cell ionization modeling, which tells you that every time, the way you calculate the ionization, you assume a constant density, constant temperature gas. And the reason that's not crazy is because we do this calculation based on every single cell in our simulation. And within the cell, we know nothing about the internal structure of the gas. So it's all right to do a single cell assumption. And again, this is the biggest problem I think we have. We assume ionization equilibrium, but really there's not much we can do as is. So we build a cloudy grid that has these lovely parameters. And effectively what we're saying is that we account for redshift, we account for metallicity, we account for temperature, for the AGN intensity, and for the number density of hydrogen or the density of the gas. And then what you can do is interpolate every single cell in this giant grid. And it's not a crazy thing to do again. And this is what you get. It's not pretty. But on the top, we have the covering fractions of 3 species. So we have neutral hydrogen, which people love. We have C4 and O6. And the idea behind these 3 species is they probe 3 different types of gas. So you have your hot gas, your warm gas, and your cool gas in the CGM. The column density thresholds that we've picked are observationally motivated in this case for the CGM. And in the lower panel, we saw the star formation rate. And in the middle panel is the AGN luminosity or bolometric luminosity, color-coded by the red is when the quasar feedback is on, and the black is when the radio mode feedback is on. And if you look at it at first sight, after the merger, all of your species are almost gone. You basically don't see them. So what we're saying is that the covering fraction of any species you want after the merger declines, and it declines significantly. And that's concerning because you're ionizing your whole CGM, and that's problematic. However, the only way to test this is for observers to look at galaxy mergers and look at their CGM and see if that's true, or look at AGN active galaxies or AGN hosts and look at their CGM and see if that's true. And there are surveys for both of those using COS, so we'll see what they get effectively. But our first hunch is that our AGN scheme is too effective at ionizing the gas. And the problem here is that the only gas that increases in covering fraction is O7. And O7 is too hot to be in the CGM. Now, there's another issue. Maybe the resolution is a problem, and we've rerun this simulation with 3 resolutions, and you see generally the same qualitative effect. So our AGN is really too powerful that it ionizes everything post-merger. That may be a problem on our side, which we kind of need to fix. Now, the problem is that this AGN model has been calibrated, of course, as every AGN model is in zoom-in simulations, to match your stellar luminosity function. Great, but we have like a second-order issue here, which is we're not matching anything effectively in the CGM. So when your quasar is on, you're just too hot and too powerful. Now, I talked earlier about this significant dip in the gas. So it was about 11 to 12 gigayears is when your gas starts to disappear from the CGM. And that's your densest gas. So if you look at 11 to 12 gigayears, which is right here, you have a 10 to the 44 ergs per second AGN that's on, and it's on in a radio mode. And our radio mode feedback is, the way it works is you launch these bubbles that rise buoyantly in the CGM at about 50 kiloparsecs away from the galaxy. So what that's really doing is you're putting a lot of internal energy into these gas cells at 50 kiloparsecs, and you're letting them rise buoyantly. So right around here, is you launching significant winds that originate in the CGM. So if you're looking at the total covering fraction of the gas, you see a lot of this gas just disappearing from your CGM at that point. And that's purely because of the implementation of the radio mode. It's just crazy effective at launching this gas. So we see this decrease. So again, it's not too crazy or surprising. Now that is not seen if you look at lower column density gas, simply because that's the diffuse ambient medium that's always going to be there. So you remove some of it and you fill the rest of it in quite easily, in fact. Now, there is another issue, is that if you run a correlation between your covering fraction and the AGN, you see significant correlation. Effectively, if you just eyeball it and look at every increase in this AGN activity corresponds to decreases in the covering fraction, which is shocking and surprising that your AGN is this effective at varying this whole ionization of the CGM out of to 100 plus kiloparsecs. So we think we have an issue with the implementation of the AGN. However, that we're going to leave for future work to investigate what's a good AGN model to run with. Maybe the solution is to run with many AGN models that are abundant in the literature and see what different people see. But in general, our simulations are showing that you have a significant increase in the CGM ionization. So you can look at higher ionization species, hotter gas, which is kind of a problem for observers just because of the wavelength range that you can observe. But also, the other thing you can do is just try different simulations and see what we're getting. So, yes.
At that point, and then no sort of higher peaks in the ground, is it a merger?
Yes, so this is where the merger happens, right? So you have your significant increase, and now you can pick other mergers that are not as clean. So in our case, you have 2 large galaxies, and you have 1 dwarf coming in, which does not affect you. Yes, so this is the merger, and we actually force our sample to have 1 merger and no major mergers after. So there is a minor merger that concludes somewhere around here, and you can see flickers as the stars fly in. But really, you've consumed a lot of your gas, but still, like even here, this peak is more than 10 solar masses a year. So this is still affecting your star formation. One thing I should have mentioned is this specific galaxy, that 2 galaxies that are merging have a significant reservoir of dense gas. So you have gas that's denser than like 10 to the negative 3 per centimeter cubed, and enough of it that when you merge, you have a starburst effectively, not just an increase in your star formation. Now, if you look at other galaxies, things are not crazy. So just to put this in perspective with what other people are doing, we know that the metals are out of ionization equilibrium if you have an AGN active. And Seegers et al. 2016 showed this. Well, they didn't show this. They showed that the metals are out of ionization equilibrium. Also, we know that shocks can heat your gas. So Cox in 2006, a couple of publications showed that your outflows can shock and heat the gas, which is also a thing, and it could be effective. And more recently, there's a fire paper. Savard et al. Showed that there's a lot of UV flickering, effectively, over variations in these massive outflows if they are produced from star-forming regions in the fire galaxies that they've shown. So there is probably a non-consensus on how the ionization is done in simulations, but also in observations. So we can't reconcile this yet. However, we do have an issue on our end, which is this over here, that you're killing all your ionization species, which is very concerning, really. But hopefully we'll be able to fix it in future iterations of our AGN model and feedback. I would like to summarize some of the main results that we see, at least qualitative results. So we see that the merger really increases the size of the CGM. If you determine some metric to measure the size, it increases your covering fractions overall for most species, and they are increased for a good number of 4 or 3 or 6 gigayears, depending which species you look at, but for many gigayears post-merger. Also, your density profile becomes shallower, which translates into this increase in the metallicity profile of the gas, and that metallicity profile increases for a large distance, more than 200 kiloparsecs for a good time after the mergers for, in fact, 6 gigayears until redshift 0 in our merger. We have an issue of increasing the covering fractions of highly ionized species. That may be really observation motivated. So Rongman Bordeloy from MIT is leading a cost pairs survey. So we'll see if his results kind of match what we see in our, if we match what the observations show, we shall see. But we also see that the only place that these low ionization species actually survive are in self-shielding regions, which may not be the case because we actually see them in normal galaxies. So that's really concerning for us that they only survive in self-shielding regions in our simulations. Nonetheless, that's what we're showing. So in the future, there's a few things that we're planning to do is to compare our results to Rongman's results. Moreover, we're running a larger suite of these of mergers to look at the properties of the orbital properties of the mergers. And hopefully in the future, we can also investigate different physics models and their effect. The way we're selecting our new suite is by putting more constraints on the progenitors of the mergers, such that when we merge the galaxies, hopefully the only effective drivers of the differences will be these orbital parameters of the merger, and we can narrow down what that merger does for the CGM, because we know that the orbital properties can affect how wide your galaxies, basically your pericentric passage. They can affect how much tidal tails you make, how much outflows you make, and so on. So with that, I'd like to thank you all, and hopefully we can have a nice discussion after.
Yeah, questions?
Since the AGN is the thing that you think is causing your ionization problems, can you describe a little bit more description there? So I guess whenever gas funnels to the center of the simulation where the galaxy where you have your AGN, it's increasing its emission a lot. How does it switch from the radio to the quasar mode? What is the description there?
For sure. So basically, you calculate your AGN accretion rate based on the local density. So you have some Bondley-Hoyle, Littleton kind of Eddington limited accretion in the central region. And then you accrete the gas, and then you decide what the luminosity of the AGN is, right? So if you are in radio mode, you basically, it's basically your ratio of the accretion rate to the Eddington rate that tells you if you're in quasar or radio mode. And then if you're in radio mode, your feedback is by launching the bubbles. If you're in quasar mode, you just affect your local medium by dumping a lot of energy into it. But then there's another a secondary issue, which is this radiation of the AGN. So the radiation from the AGN is always calculated, right? So you have some bolometric luminosity for the AGN. Doesn't matter if it's radio mode or quasar mode or any kind of mode. And then what you do is you say, okay, how far am I from the AGN? And you calculate some intensity at that distance, and then you associate that intensity with the gas cell. And you use that to change your cooling and heating timescales. Yeah.
You mentioned on the number of systems observed with a quasar in the background is small. What is the number?
Oh, mergers and
No, so when you're going to measure actually the equivalent weight for
Yeah.
one oxygen, the CGM, you were mentioned that there are surveys right now.
yes, there are many surveys out there.
You also mentioned that there are systems where you have.
Exactly. So okay. So all the surveys that have targeted galaxies right now have targeted galaxies. So for example, there's COS halos that targeted L-star galaxies that are isolated. There's COS dwarfs that are isolated, and so on, right? And there's many COS surveys that have done that. But what we're doing is mergers. So the closest to what we're doing would be COS pairs, which is led by Rongman Bordeloy, and they have, I think, 11 kinematic pairs. So that's all you get from all the SDSS pairs cross-correlated with all the quasars we know. You get 11, and that's it. So the numbers are really low. if you do that. So that is an issue that these observers have. Yeah.
Feedback models are tuned to decrease the star formation rates you observe. In doing that tuning, do people try to match it using isolated systems? Because what I'm thinking is that in your case, every time you do a minor merger, the star formation rate jumped by a factor of 10. And so if the tuning of the feedback parameters is in a totally isolated system, then you're naturally going to do perhaps tune higher than you need to in the real universe where mergers are occurring and increasing the star formation rates by a bit.
So this is a okay. So this is not like my area of expertise, but I'll try to answer it. And I'm being recorded, so I have to be careful of what I say. So the way you tune, or my understanding of the way you tune these AGN and star formation models is that you have a stellar luminosity distribution for galaxies, right? And you have your high end, and you have your low end, and you have your knee. So your knee is like L-star galaxies, great. And then your high end is these massive galaxies. So you need to kind of shut off the growth of those. So to fit that line, to fit that part, you basically turn on your AGN, and you just heat the gas, kick the gas out, and you get that right. So you tune off these parameters just to get that end right. And then on the lower end, it's stellar feedback that's more effective. So you tune on and off the effect of stellar feedback in whichever feedback mechanism you're using, and you start to get that lower end right. And then what you end up with is a stellar luminosity, like galaxy luminosity function that fits what we observe. So that is.
And is that tuning done in local simulations where you have the ability for galaxies to interact with each other?
Yeah, it's done. So this is the thing, is that this is done in cosmological simulations where your galaxies can do whatever, right? But still, mergers are a minor fraction of your normal galaxy. So if you count all the galaxies, the merger fraction is really low. So maybe that is an issue, but like we know for sure that we're not getting everything right? Like, because even the sizes of the disks, for example, in galaxies, cosmological simulations have issues reproducing and so on. So there is a motivation why we think our physics model is right. So Grand et al. In 2017 used this in what is now the Auriga sample of galaxies, and they basically run zoom-in simulations of Milky Way-like galaxies at redshift 0, and they're able to reproduce a lot of properties of the galaxies, like the disk sizes, disk warps, the metallicity profiles of the galaxies, luminosity profiles, and so on. So this is an extra motivation that we have a lot that we're getting really right. So this must be a good enough physics model for now. Now the problem is when you go to the CGM, now there's a lot of issues. When you go to the ionization, there are two issues. There's the simulation, but then there's the post-processing that we're doing. And we know for granted we're not doing the post-processing right because the observers have the same issue, right? Yeah, you see the universe and you try to kind of go backwards from the ionization to normal gas, and you have that issue. So we know that is not fully right. And now the way you tune your models, this is kind of a, depending who you ask, I think you would get different answers because there are tons of models out there, and they're so different, yet they all get something right. And people tune them differently, yet I think the common way to tune an AGN/star formation feedback is using a galaxy luminosity function. Yeah.